Okay, so here's this different proof. It's due to a mathematician at Caltech named Tom Apostol, and please, when we start writing, remind me to zoom out.
Okay.
So it says, here's an isosceles right triangle with integer sides. Now, if this is an isosceles right triangle, it's got to be similar to the 1, 1, root 2 triangle.
Yeah, so it'll be in that form.
Yeah, so the ratio of the hypotenuse to one of the sides is the square root of 2. But if the square root of 2 is rational, then we could have one that had integer sides. So he's making the same assumption. Let's start out that we have integers. Then you can create a new smaller one, which is shown right here. It's also an isosceles right triangle that has integer sides. Okay, so what's the problem? If this ends up being true, if you start with one that has integer sides, you can always create a smaller one that has integer sides. So what's the problem?
Eventually he won't be able to repeat this process anymore.
Why not?
Because if you start with finite integers, eventually you'll get down to a point, say you have the 1, 1 and an integer here, and you can't create a smaller triangle.
Right, it's the same problem. This is called proof by descent, or sometimes infinite descent. What do you think are, before we try to prove this, what do you think are the geometric ideas that we're going to need to do this proof here, to show this construction?
Probably similar triangles, because we're creating another smaller triangle, and that triangle has to be, we have to show probably that's similar to the large triangle.
Okay, yeah, we can actually see this reasonably quickly. So why is this triangle here a 45, 45, 90 triangle, or an isosceles right triangle?
So the angles are all the same as, we have the 45-degree angle, the 45-degree angle, and the 90-degree angle.
Yeah, why though? Why did we get those angles?
Well, one angle is shared with the larger triangle, and I guess you'd create this 90-degree angle by forming a perpendicular and dropping it down to the other side.
Great, perfect. Okay. And we do this, we make this side length the same as this side length just by assumption, because the hypotenuse has to be longer. So
yeah, we know this will be longer.
Okay, so now the tricky part is trying to understand why this side length here has to be the same as that one. Do you see why that's true?
Well, not immediately, no. So might have something to do with maybe this sort of circular edge here.
Okay, yeah.
Because this is a slice of a circle.
That's a great idea. So there is a circle, or at least a slice of a circle hiding in there.
So these will be, since these are the same side length, then if we could show that maybe we could slice here and create congruent triangles, maybe?
Oh, well, that's actually a really good idea. You could create, if you drew a line in here, maybe you'd get two congruent right triangles. Yeah, that's a really interesting idea. There's another little piece about that circle that comes into play here, actually.
See. It's an eighth of a circle, so.
Well, that's true, but it's not. It's actually just the fact that it's a circle. It doesn't matter what that angle is. There's something here that would always be true, no matter what that angle is with a circle.
It would always be possible to create lines like this for any wedge of the circle, I guess.
Yeah, it would. Well, I'll tell you what. Let's come back to it at the end. We can take a different approach to proving this. We'll come back to it again. There's a really important geometric idea hiding here. I know it's been a couple of years since you studied geometry, so it's not at the front of your mind, which is fine. We'll come back to it and talk about it in the fourth video. But let's do a computation here.
Okay.